We can also define the potential energy of the elastic spring. We call it the elastic potential energy. This, for example, if we have a spring, an ideal spring that follow the Hooke's law attached to an object, and if we apply the first we have to define the system. So here the system is the spring and the object. This is the system. The system is the spring and the object. Now, if we apply the external force, to the system, we know that we have the restoring force from the spring. Okay. And now, if we do the quasi-equilibrium process, that is, we apply the external force to the system and move this object very slowly. And if we move the object from the position xi to the final position xf, since we do the quasi-equilibrium process, we have that the applied force is approximately equal to the restoring force, or force from the spring is equal in magnitude to the restoring force, but has the opposite direction. So approximately equal to the kx, right? So as we have done the detail before, we have that W work from the external force is equal to the half of kxf square minus half of the kxi square. Okay. Now we move the object from the initial point, and we assume that the object is at rest at the initial point. We move it very slowly to the final point, and at the end the object is at rest at the final point. So it means that in this process there is no change in kinetic energy, that the K is 0. So we cannot apply the work kinetic energy to this situation. However, we know from our experience that once we pull the object to the final position and then we release the object will move back to the equilibrium point, and we have the we have the kinetic energy. So it means that our process that we pull this object from the initial to final point is something like we put some kind of energy into the system, and this energy will change back to the kinetic energy. Okay, when you release it, it moves back to the equilibrium point. It means that we have the kinetic energy. And by the same concept as the gravitational potential, we can define the elastic potential energy. Elastic potential energy is equal to half of the k x squared. So it means that we can write down this external work from the external applied force as delta US. So this is the definition of the elastic potential energy. Again, we can say that the work done by the external applied force will give the potential energy to the system. This potential energy will store in the system until we release the applied force, and after that the potential energy will transform to the kinetic energy and so forth. It means that the potential energy can transform to the kinetic energy, that is, it makes the object move. And also when the object moves maybe to the equilibrium point, but it has some velocity, it can move further away from the equilibrium point, but it will move slower and stop at some point. It means that the kinetic energy will change to the potential energy also. So we can have the transformation between the kinetic energy and the potential energy. The relation between kinetic energy and potential energy can be visualized or can be explained using the energy bar chart. In the energy bar chart, we categorize the kinetic energy, the potential energy, and the total energy. The total energy here is defined as is the kinetic energy plus potential energy. We also call this the total mechanical the total mechanical energy. We will explain the reason of this name soon. In this chart, you can see that we first take the object to the equilibrium point of a spring, and then we push the object. We push the object, which means that we compress the spring also, and it means that when we compress the spring, we have the potential energy from the spring here. And when we reach the maximum compression, after that we release the object, and the potential energy in the spring change to the kinetic energy. So you can see that first there is nothing, there are nothing, but when we start pushing the spring, the kinetic energy increase. But if we do it in a quasi-static or quasi-equilibrium process, it means that the object moves very slowly, so there is no kinetic energy. We increase the potential energy to the maximum value when we reach the maximum compression, and after that we release the object, and the object starts to move to the right. The potential energy decrease, but the kinetic energy increase. So we have the potential energy decrease to its minimum value, which is 0 at the equilibrium point, and after that we have only the kinetic energy. If we sum up the potential energy and the potential energy and the kinetic energy after we release the object, we can see that the total energy is not changed. After we reach the maximum compression and start to release the object, we can see that the total energy is not changed. We will discuss this in the next chapter about the total energy. But now you can see in this figure everything is 0. In this figure everything is 0 because you do nothing to the system. But when you start to push the spring, the potential energy increase, and also the total energy increase, because now the total energy is equal to the potential energy. There is no kinetic energy in this when you move the object very slowly. Okay. And the total energy will reach its maximum value. Will reach its maximum value when the potential energy reach its maximum value here. After that, it's not changed. Okay.